Okay, so let me go back to. Okay, so that's basically the relationship between molecular mass and molar mass. All right. So what was I about to say? Oh, okay. So now we're going to go back to the number, the mole, the number which I mentioned before, the large number, which represents the number of items in 1 mole of anything, right? So that number, by the way, I don't think I told you the name given to that number. It's called Avogadro's number. Avogadro's number. And that is 6.02 times 10 to the 23 items, and the items could be molecules, atoms, per mole. All right, so that's Avogadro's number. Okay, why is this doing this? It should be -1 here. I don't know why this is acting up. Okay, so this should be -1 here, all right? In fact, let me do this. I don't know what's going on here. All right, so that's basically Avogadro's number. So we have now, based on what we have discussed so far, established a relationship between Avogadro's number, the mole, and the molar mass, right? And basically, what I'm going to do is put 1 mole in the middle here, and that would be equal to the molar mass in grams. And over on this side, I'm going to put this equal to 6.02 times 10 to the 23 items, right? Molecules or ions or atoms, all depends on what you're referring to, all right? So that's a relationship between these 3 terms, all right? So we can use this idea to solve certain problems. And in fact, the next assignment I'm giving you will deal in the first part with these kind of problems. So I'm just going to make up one here. So let's say you're given 5.92 grams of, let's say, mercury, right? In fact, let me clear this and then start from the top because I'm going to need a space. So let's say you're given 5.92 grams of mercury, and you're asked to determine the moles of mercury that's equivalent to that mass, all right? So the first thing you would do is start off with the 5.92 grams of mercury. And what I'm going to do is multiply by the appropriate conversion factor, which relates mole to grams. Now, of course, you have to be careful where you put the different terms. So as the numerator, I'm going to put 1, well, not 1, but mole of mercury. I'm just concerned with the units for the time being. And then down here, I'm going to put grams of mercury, all right? And then I would go to the periodic table. I don't know what these numbers are. To look for the molar mass of mercury. Okay, where's mercury? Hg, okay, 200.59. So I'm going to put 200.59 here. And here I'm going to put 1 mole, right? And then I will do the calculation. So that would be 5.92 divided by 200.59. And according to my calculations, the answer becomes 0.0, okay, round out to 3 sig figs, so 0.02 0.95 moles. All right. And that's it. That's how you go from grams to moles. All right. Any questions? Any questions? Now, what if you're given this 5.92 grams of mercury and you're asked to convert that to number of mercury atoms? All right. So the way you go about doing this is that you start off with what you're given. You're given grams of mercury, and I would convert to moles of mercury, just like I did in the first example above. All right. But the question is asking not for the grams of, I'm sorry, not for the moles of mercury, but for the number of mercury atoms. So you need another conversion factor, which would allow you to convert from moles of mercury to the number of mercury atoms, right? Now, for this conversion factor here, you're going to need a molar mass, right? Which is what we did here. So this conversion factor is going to be used to carry out this conversion right here. But to go from here to here now, we're going to need Avogadro's number, all right? So this is how you set this up. You start off with what you're given, the 5.92 grams of mercury, and then you multiply by 1 mole of mercury above, and the molar mass of mercury, which is 200.59 grams. And then you multiply by the conversion factor, which allows you to convert from the moles to the number of atoms. Now, before I do that, let me just show this cancellation right here. So the question now becomes, what goes up top here, what goes down here? Well, the mole of mercury unit would go down here, and the number of atoms would go up top here. And therefore, in terms of the numbers, 1 would go here, and Avogadro's number would go here, all right? Because remember, Avogadro's number represents the number of, in this case, atoms present in 1 mole of mercury. And then we do the number crunching. So let me do that here. 5.92 divided by 200.59 times 6.02 times 10 to the 23. Okay, so according to my calculations, rounded off to 3 sig figs, the answer becomes 1.78 times 10 to the 22, and the units would be mercury atoms. All right, and that's basically how you do that. Okay, any questions about this example? Any questions? Any questions? Any questions out there in Zoom?
No, sir.
Okay. And what I just did just now applies not only to elements, but can also apply to compounds as well, right? Same idea. In fact, let me create another example here. So let me get rid of this here. And let's say you're given, now this is a bit of a reverse kind of situation. Let's say you're given 5.79 times 10 to the 24 molecules of water. And let's say you're asked to find the mass equivalent to that number of molecules, all right? So what we would do is go from molecules of water and convert that to moles of water. In order for us to do that, we're going to need to use Avogadro's number. And then we go from moles of water to grams of water. And in order to do that, we're going to need to use the molar mass of water, all right? So we're going to start off with what we're given, 5.79 times 10 to the 24 molecules. And we're going to multiply by a conversion factor, which involves Avogadro's number. The number of molecules will go down here, and 1 mole will go up top. So that would be 6.02 times 10 to the 23, right? That would go down here. So the molecule units will cancel out. And by the way, this is molecules of water. So let me put that here as well. And then the next conversion factor is where we convert from moles of water to grams of water. So in order for us to do that, we need a molar mass. How do we get a molar mass? We go to the periodic table, we add up the molar masses of hydrogen and oxygen, You have to multiply the molar mass of hydrogen by 2, add it to the molar mass of oxygen. We did that already, so I don't need to repeat that. There should be mole of water here. So down here, you're going to have 1 mole of H2O. And when we did that earlier, we got 18.02 grams of water. And that's basically the setup right here. The moles of water will cancel out. So your final units would be grams of water. So let me do that here. 5.79 divided by 6.02 times 10 to the 23. And then I multiply that by 18.02. And according to my calculations, rounded off to, make sure I'm doing this right. Something doesn't look right here. 5.79 times 10 to the 24. I think I forgot to include the times 10 to the 24, divided by 6.02 times 10 to the 23, and then multiply by 18.02. Okay, now this looks more like it. Okay, so according to my calculations, the final answer is 173 grams of water. All right, and that's how you do that. All right. Any questions? Any questions about this? Any questions? All right, so based on what we have just looked at, you guys should be able to attempt the first part of this assignment. Pass down. Pass down. That's for you. And this is for you. And for you guys out there in Zoom, I think I have already published it, but let me make sure. So let me go here, let me go here, let me go here. Oh, so let me just say that based on what we have covered so far, you should be able to do parts 1 and 2. So let me publish, if I haven't done so already. Okay, it's already published, folks, for you guys out there in Zoom. Assignment number 8 is there, so make sure you download it. And I want you guys to get started on it. I'll give you some time because I want to proceed to some other topics. But I just want to make sure that you guys have an understanding as to how to answer these questions. Now, let me just say that for part 1, I want you to use the tables that I've provided in Canvas because you're going to need that to calculate the molar masses in each of these cases, right? So you can bring it up on your devices and use that to calculate the molar masses for these different compounds. Remember, the units of molar mass is grams per mole, all right? Units of molar mass is grams per mole. All right, so you can get started on that. If you have any questions, feel free to ask.
So I have a question.
Mm-hmm.
I already submitted the entire assignment on Canvas, but I had a question about one of, yeah.
Wow.
I had a question about one of the answers that I had. It's for question number 9. It says how many moles are in 19.8.
All right, hold on 1 minute. Let me see if I can bring it up on the screen here.
Okay.
Oh, downloaded the wrong one. Should be chapter 8. Okay, you said question number 9?
Yeah, question number 9. It's about how I rounded it off pretty much.
You're talking about this one?
Yeah, that one. I did the 19.8 times the 10 to the 24th.
Mm-hmm.
And then I put the parentheses 1 mole over Avogadro's number.
All right, hold on. Let me write down what you're telling me.
Okay.
So you start off with
the
19.8 times 10 to the 24 molecules
of C6H12O6,
right?
Mm-hmm.
And then you multiply by what?
I did the 1 mole over the Avogadro's number, so the 6.02 times the 10 to the 23rd.
Okay, and then?
And then I did parentheses, and then I did the molar mass of.
Okay, you didn't need to do that
Okay. No.
because the question is asking for how many moles.
Okay, so then I wouldn't have to get the mass of the actual.
No, you don't need a molar mass.
Okay.
No, you're going to
So
need a molar mass for this part here. So for this part here, this is all you need. So all you have to do is divide the 19.8 times 10 to the 24 by the 6.02 times 10 to the 23. And whatever you get there, that would be the answer.
Okay, even if it has the 10 to the whatever power.
Well, let me do this. If I were to do 19.8 times 10 to the 24 divided by 6.02 times 10 to the 23, the answer I got is 32.9 moles of C6H12O6. That's the answer I
So
got.
would I be able to fix that and then just resubmit my
Yeah, no problem.
Okay, thank you. And then I think that I did the same thing for, let me see here, for there's another one that I did that for that I want to make sure that I just have to fix it. I did that for question number 4 too. Would I just
Question number 4?
Yeah, so I would just do the 3.4.
Let me see. Hold on. Let me see. Question number 4. Question number 4. Question number 4. Yeah, it's pretty much the same thing.
Okay, so then I wouldn't do the molar mass of the actual chemical.
Yeah, right. Because all the question is asking for is the moles.
Okay.
If the question was asking for the grams, then you take the next step of using the molar mass.
Okay,
You see what I'm
perfect.
saying? All right. Let me see. Somebody said something in the chat. Oh. Thanks for letting me know that, Mr. Baldus. I'll make sure I'll change that right now. I didn't realize. Okay. Okay, Miss Hersey, yes, you can resubmit it. So if you have submitted it already, you can resubmit it after making whatever changes you need to make. All right. I didn't realize that I had published it before. Usually I don't publish it until the day of class, so that's kind of my fault. Even though I do appreciate that you guys try to go ahead and attempt those problems. So okay, so let me see here. Oh, so from what I see here, 1, 2, 3, 4 students have submitted assignment 8. But you can resubmit it after making changes. If you have, based on what we have talked about here, if you have realized that you have made some errors, I have no problem with accepting it after you have resubmitted it. All right, so that's fine by me.
I do have one more question.
Yes, ma'am.
But it has to do with empirical formulas, which I know you're not there yet, but it's just about the rounding off. So for the empirical formula, whenever you get the number, I just wanted to know the rule for how to know how to round off the numbers.
Okay, very good question. So when it comes to rounding off, if the number, after you get to that stage where you're trying to find the simplest ratio, if the number is within 0.1 of the next integer, then you round off to the nearest integer. So for example, let me just use this right here. So let's say at this stage you got 2.9. Then you basically round off to 3. Or if you got 4.1, you round off to 4. All right. Now, if you got something like 2.5, you cannot round off to 3. All right, because 2.5 is too far from the nearest integer. What you'd have to do is somehow multiply this 2.5 by an integer to convert it into another integer. And in this case, you'd multiply it by 2, and you're going to end up with 5.0. You see what I'm saying? And I think I made mention in the videos. In fact, I know I made mention in the videos that there are certain numbers where you can multiply those numbers by integers to get the nearest integer. Anything with 0.5, like 1.5, 2.5, 3.5, you'd multiply those numbers by 2. Anything with 0.25, like 1.25, 2.25, you multiply that by 4. Anything with 0.75, like 3.75, 2.75, you multiply by 4. Anything with a recurring 3 after the decimal point, like 1.33, you multiply by 3. And what else? Anything with a recurring 1 after the decimal point, like 2.1, you multiply by 9. And I think that's the ones that I can think of right now. And then there are some others where you simply have to use trial and error. All right, but these are like the more common ones that you'll encounter at this level. So I hope I have answered the question.
Yes, for the last like question on the worksheet for the empirical formula, I had one of them that ended with like a 5.8, so I just rounded it off to 6. I wasn't sure if that
Which
was
one is that?
It's the very last one. Let me
The very
see.
last one?
The number 5 on page 9.
This one?
Yeah.
Okay, I'd have to work this to see what, because I'm not saying that you're wrong, but I don't know. I'd have to see what you did, or I would have to work it out myself. Here you go, sir. I'd have to work it out myself to see what you're referring to.
Okay, no worries.
Okay. What's your last name? Got you. I'm going to give you guys until about 11:45 to work on these, and then I want to move on to some other things. All right, so Okay, let me proceed. Let me go back to sharing my screen to talk about what this chapter is really about. And that has to do with this whole concept of percent composition of compounds. And straightforwardly, it's rather simple. Oops, what did I do? Okay, it's rather simple. Basically, when we're talking about the percent composition of a compound, we're talking about the percentage of each element present by mass present in the compound. And there are a couple of ways that we can do this. We can determine this figure or numbers. We can determine it based on the formula for the compound. So if you're given the formula for the compound, you can determine the percentage of each element present. And I'm going to use, as an example, water again, right? So if you want to find the percent composition of water, it's very simple. Basically, what you'd have to do is find the molar mass of each element present and divide it by the total molar mass of the entire compound. So let's say we determine first the percentage of hydrogen present. Then we take the molar mass of hydrogen, which is 1.008 grams per mole, and we multiply that by 2, and we divide that by the total molar mass of the compound, which we calculated earlier, it'd be equal to 18.02 grams per mole. And that's it. Well, not quite, we have to multiply by 100%. So if we do that, times 100%, according to my calculations, you're going to get 11.19%. And then in the case of oxygen, we take the molar mass of oxygen, 16.00 grams per mole. There was only one of them, so that's all we need for the numerator, divided by 18.02 grams per mole, times 100%. And according to my calculation, that would be 16 divided by 18.02. That would be equal to times 100%. That would be equal to 88.79%. All right. And when you add these two numbers together, you should get, if not 100%, a number very close to 100%. All right. So that's pretty much how you determine the percent composition of each element based on the formula. Now, what is more challenging is the reverse. In other words, if you're given the compositions, right, of each element, how would you determine the molecular formula for the compound? All right. That's a bit more extensive, and that's what I'm going to do here. Now, how am I going to do this? Let me go back to the PowerPoint that I covered in the videos, and I think there's one example that I worked on. Let me see. Okay, so let's look at this example here. In fact, let me copy and paste this onto my writing pad here. Okay, what is happening here? Why does it look like that? All right, you know what? Let me go back to the PowerPoint and work from there. I just think that I might be, I don't think I'll have enough space down here to work with, but I'll try. Okay, so let me go here. All right, so in this question, they gave you the percent composition of each element present in this compound, right? 56.58% of it is potassium, 8.68% of it is carbon, 34.73% of it is oxygen. And the question is asking for you to calculate the empirical formula. Now, I think we covered the difference between the two, but just in case I haven't, the empirical formula is basically the simplest ratio, or the formula that gives you the simplest ratio of all the atoms present in a molecule. So let me just give a quick example. there's a compound known as glucose. The formula for that compound is this right here. All right? That's a molecular formula. Right? That tells you exactly the number of atoms of each element present in one molecule of the compound, right? So one molecule of glucose, according to this formula, will contain 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms, right? The empirical formula for this compound is CH2O, right? Now, the relationship between these two, obviously, is that if you multiply each of these subscripts by, in this case, 6, you're going to get a molecular formula, right? And that's because the empirical formula gives you the simplest ratio of the atoms of the different elements present in a compound. There's a 1 to 2 to 1 ratio between the carbon, hydrogen, and oxygen atoms, right? So that's the difference between the empirical formula and the molecular formula. The empirical formula gives you the simplest ratio of the atoms of each element present in the molecule, while the molecular formula gives you the number of atoms of each element present per molecule. And the relationship between the empirical formula and the molecular formula is a whole number relationship. In other words, in order for you to get from the empirical formula to the molecular formula, you have to multiply by a particular integer. And that integer could be any integer literally, from 1 to whatever, right? In some cases, the integer is 1. For example, in the case of water, the molecular formula is H2O and the empirical formula is H2O, right? In the case of water, they're both the same, right? In other cases, like in the case of glucose, you have to multiply by a particular integer. It could be 6, 5, 4, 10, whatever, all right? Okay, what this question is asking for specifically is the empirical formula for this compound. So let me erase what I just wrote here and get started on this problem. Now, personally speaking, I like to do this in a tabular form, right? So what I'm going to do here is write down potassium, carbon, and oxygen at the top of this table. And then the first row below it will be the respective masses of each element, right? Now, the question did not give us the masses, right, of each element. The question gave us the percentages, right? So what we can do is assume, for all purposes, for the purposes of solving this problem, we can assume that we're working with 100 grams of the compound, right? 100 is a nice round number because if we assume that we have 100 grams, that means that each of these values would represent the mass of each element present in 100 grams, all right? So the first row here, I'm going to record the masses, assuming that we're working with 100 grams. So therefore here, we're going to have 56.58 grams. Here, we're going to have 8.68 grams. And for the oxygen, it's going to be 34.73 grams, all right? So that's the first row. The next step is that we convert each of these masses into moles, right? So if you remember what we talked about before, in order to convert from grams to moles, we have to divide each of them by their respective molar masses, which you would get from the periodic table. So in the case of potassium, it's 56.58 grams, and we multiply by 1 mole over the molar mass, and the molar mass of potassium is 39.10, I would say. I think that's a value that's in the periodic table that's posted in Canvas. So I'm going to put 39.10 grams, and we'd have to work that out. We do the same thing in the case of carbon. We take the 868 grams and multiply by 1 mole over 12.01 grams. And in the case of oxygen, 34.73 grams, we multiply by 1 mole over the molar mass, which is 16.00 grams, all right? And we have to work out each of these. So let me do that now. So for the first one, it's 56.58 divided by 39.10. And what I got is 1.447 moles. And then in the case of carbon, it's 8.68 divided by 12.01. And I got, in this case, 0.723 moles. And finally, in the case of oxygen, 34.73 divided by the molar mass, which is 16. And I got, in this case, 2.171 moles, all right? So that's what we do at this juncture right here. So the next step, what's the next step? The next step is that we look at these numbers here and we identify which one of these would be the smallest, because the next step, what we're trying to find is the simplest ratio. Right? So how do we find the simplest ratio? We look at the 3 mole values that we just calculated, and we divide each of those values by the smallest, right? So this is the smallest right here, this one right here, all right? So we divide this number, and this number by the smallest value. So in the case of potassium, it's 1.447 moles divided by 0.723 moles. And we work that out. Now this divided by itself will give you 1. And then in this case, we divide 2.171 moles by 0.723 moles, and we work that out, right? So for the potassium, it's 1.447 divided by 0.723. And according to my calculation, this works out to be equal to 2.001. And then for oxygen, it's 2.171 divided by 0.723. And according to my calculations, this works out to be equal to 3.002. Now this goes to the question that the young lady, I don't remember who, somebody out there in Zoom, she asked, right? What do we do? How do we determine the extent to which we round off the final answer here? Because remember, the simplest ratio must have integers, right? In this case here, as you can see, 2.001 is very close to 2. So we can simply approximate that to the nearest integer, which is 2. The same is true over here. 3.002 can be approximated to 3, because again, it's very close to the nearest integer, which is 3, right? So therefore, the empirical formula for this compound is K2CO3, right? So basically all these integers that we just calculated, that we just estimated, will serve as the subscripts in the empirical formula. And that's basically how we do that particular problem, all right? Any questions about this? Any questions? Any questions? All right, how much time do we have left? Because, all right, so sometimes things don't work out as smoothly as what we just did, especially when it comes to this last stage right here. And I think the next example is probably one like that. So let me do this one here. So in this case here, they gave you the percentages of 2 elements. There are only 2 elements in this compound, nitrogen and oxygen. So we're going to take the same approach, construct a table. And again, we're going to assume 100 grams. So that means that the mass of nitrogen would be the same as the percentage, which is 25.94 grams. And the mass of oxygen is going to be 74.06 grams. And then as we did before, we're going to calculate the moles. So if you remember what we did at this juncture, we multiply that by 1 mole over the molar mass of nitrogen, which is 14.01 grams. And then for the oxygen, we multiply that by 1 mole over 16.00 grams, all right? So let's do the number crunching here. 25.94 divided by 14.01. So according to my calculation, this works out to be equal to 1.852 moles. And then in the case of oxygen, 74.06 divided by 16. And according to my calculation, this is 4.629 moles, all right? Then, if you remember what we did the last time, we find the simplest ratio. And how did we find the simplest ratio the last time? Can anybody tell me? We divide right through by the smallest. So which one of these two are the smallest? This one, right? So this divided by itself will give you 1, and then we divide 4.629 moles by 1.852 moles. And when I do that on my calculator, 4.629 divided by 1.852, very interesting. This is what I got. 2.499. All right. Now, unlike what we did in the previous example, we cannot simply round this off to the nearest integer, right? Because 2.499 is too far from the nearest integer, right? So what we have to do is figure out in another step, what do we multiply this number by in order to convert it into an integer, right? Now, 2.499 is very similar or close to 2.5, right? And if you want to convert 2.5 into an integer, all you have to do is multiply 2.5 by 2, right? But you cannot just multiply this by 2. You have to multiply the nitrogen value by 2 as well, right? So you're going to end up with, when you multiply right through by 2, you're going to end up with 2 here, and then 2.499 times 2 gives you 4.998, which is very close to 5, right? So therefore, the answer here is that the empirical formula will be equal to N2O5. And that's how you do that, all right? And as I was explaining to the young lady, I don't know if you guys were paying attention when she was asking her question. There are certain numbers when you get to this stage, you can figure out what you multiply by in order to convert it into an integer. And I gave a list which I erased, so I guess I have to, oops, let me do this here. Let me go back to this here. So if your number at that stage that I just described is something, has something 0.5. So let's say it's like 2.5 or 1.5 or 3.5, then you'd have to multiply that number by 2 to get the integer that you want to convert it to. So this will be 7, this will be 5, and this will be 3. If your number has something like 0.25, so like for example 1.25, 2.25, 3.25, and so on, then you have to multiply those numbers by 4. All right. If your number has something 0.75, 1.75, 2.75, etc., then you have to multiply those numbers by 4. If you have a recurring 3 after the decimal point, like 1.33, 2.33, and so on, then you have to multiply by 3. If you have a recurring 1 after the decimal point, like 1.11, 2.11, then you multiply by 9, all right? And those are the ones I can think of off the top of my head. There are some others. In some cases, as I said to the young lady earlier, trial and error is that you have to employ in order to figure out what you multiply that number by to get your integer that you can use to determine the empirical formula, all right? Okay, so what I would suggest you do is, based on what we have covered, you should now be able to do not only the questions that I talked about earlier, but questions in part 3 on page 5. So you have number 1 in part 3, number 2, number 3, number 4, and number 5. And based on what the young lady told me, it seems as if number 5 deals with what I was just describing. So if you have any problems with each of these, please feel free to contact me during my office hours. I don't have any office hours today or tomorrow, but I will be available on Thursday and on Friday online. Thursday I'll be at Pacala and online. Friday I'll be online. So feel free to contact me during those times. All right. I'm going to hang around here until 12:15 because I have another class here after, so I'm not going anywhere. So if you want to stay and work on these, or if you want to leave, that's fine by me. And the same goes for you guys out there in Zoom. I'll just hang out here until 12:15 if you have any questions while you're working these problems. You too, take care. Yes, sir.
What's our next test?
Good question. I was thinking about that and I just didn't have time to look it up, but let me see here if I can look at the syllabus.
Oh, it's in the syllabus, I just know the syllabus.
Yeah, it's in the syllabus. I need to know that because I need to get that together as well. Let's see. So. Okay, so according to this, oh, the 16th, I guess I'll have to push that off because that's next week. So more than likely, it's going to be the week after the 16th,
Okay.
like the 23rd, thereabouts. Yeah,
All right, thank you.
no problem.
Have a good day.
You too. Okay, it's now 12:15, so I'm signing off now because I have to get ready for my other class. So I'll see you guys next week.